Good afternoon, folks. Thank you for tuning in to another Risk Institute online session. Today, we're really delighted to have with us the wonderful Mr. Dominik Hose, who will talk to us about his PhD research on possibilistic inference from imprecise probabilities to inferential models. The presentation will be around 45 minutes with around 15 to 20 minutes of Q&A. Please could you make sure that your mics are muted, and if you have any questions, just leave them in the chat. Before we begin though, we'd like to make a few announcements about the coming talks. So on the 22nd of February, we have Professor Zafalon Marco talking to us about causal inference, is imprecise probability in action. Then on the 24th of February, next week we have two talks. So Dr. Jasmine Scarlett will talk to us about the keys to the past and mixed methods approach to reconstructing the 1812 eruption of La Soufrière Saint-Vincent. So that'll be exciting to talk about volcanoes. And then we have some talks. We haven't confirmed the titles yet, but from Miss Ariana Casanova, I believe she's a collaborator or a student of Professor Zafalon, and Dr. Dalal Al-Raja from Imperial College. So without further ado, let me introduce our speaker. So Mr. Dominik Hose, as many of you have already met before, he received his B.Sc and M.Sc in simulation technology from the University of Stuttgart in 2015 and 2017, respectively, where he's working on his PhD for the last 5 years. He's been a PhD student working on possibilistic uncertainty quantification with imprecise probabilities under the supervision of Michael Hanss. And in January 2022, he submitted his dissertation entitled Possibilistic Reasoning with Imprecise Probabilities, Statistical, Inference, and Dynamic Filtering. So I congratulate him on that talk, on that thesis submission. And let's welcome our speaker. If you'd like to start showing your slides.
Sure. Right. Can you see that all right?
Yes, perfectly.
I'll just try to minimize this. All right. Thank you for the introduction. I'm here today to talk about part of my dissertation, which Francis just mentioned. I'm going to be talking about possibilistic inference. So it's my favorite topic, possibility theory, which I've been working on for the last 5 years. And in particular, I'll be talking about the connections between possibility theory, imprecise probabilities, and inferential models. So maybe start with a quick motivation. So what's the probability of the failure of this nuclear reactor? So this is a picture from Fukushima, where in the eyes of many, probably the risk analysis was not performed with enough due diligence, or something failed. And then there's this very nice quote that I found by our ex-chancellor Angela Merkel. So after Fukushima, it's about something else. It's about the reliability of risk assumptions and the reliability of probability analyses, because these analyses form the basis on which policymakers must make decisions. So I quite like this quote because it's remarkable in the sense that it mentions risk assumptions and probability analyses. And usually you would think that risk assumptions and probability analyses are the basis for reliability analysis, but she explicitly says that it should be the other way around. The risk assumptions and the probability analysis should be reliable. So this is a whole new source of uncertainty that she mentions here, and maybe trying to put some light into this field of uncertainty quantification. I should start with a slide, like a quick overview of nomenclature and how I think about uncertainty. So usually in engineering, at least, I think about, on the left side, you see some state of the world. So you, for example, consider a coin, and that could be fair. So let's say, for the sake of the argument, that the mass distribution of that coin is fair, and so that it lands on heads or tails with equal, well, let's say, probability. And then we have loaded coin, which is more likely to land on either side. Now then, this is our state of the world. It's supposed to be the ground truth or something. And then we can perform experiments, and we can observe the outcomes of this experiment that's depending on the state of the world. And we can see different kinds of experiments. So here, heads and tails, or just heads or just tails. Well, now you've got two kinds of uncertainty in here. If you assume that you know the ground truth, then you would try to make some statements about the outcome of the experiment. And that's usually what you would call chance, so the chance that Q1 or Q2 happens given theta 1 or theta 2. Now, on the other hand, so this would be called aleatory uncertainty because it has this natural variability or randomness, as whatever you want to call it. And then on the other hand, you may have epistemic uncertainty, which would be going the other way around. So observing some measurements or observing some experiments, collecting data, and then trying to infer the actual state of the world, the ground truth on the left side. And this would then require a theory of belief. So now traditionally in uncertainty quantification, or many people associate chance and probability theory with that. And it's kind of there's not much argument about the suitability of probability theory as a description of chance. So if you're going from the left to the right side, then probability theory is usually what you can use as your description of chance. Now, if you're going the other way around, you have this, you want to find an expression of your beliefs that you build depending on the observations that you make. And then that's a whole different story. And this is mainly what I want to be talking about, what I'm going to be talking about today. So starting with this theories of belief, traditionally you have Bayesian statistics and frequentist statistics. This is what most statisticians will know. You have frequentist statistics, which is all about confidence intervals and hypothesis tests. And then you have Bayesian statistics, which is usually about posteriors computed from priors and from likelihood functions. However, Thomas Bayes himself said, by chance, I mean the same as probabilities. So he himself says that probability was originally intended to model chance. Now, Bayesian statistics use probability theory to also model belief, which has its drawbacks and disadvantages, and I will be coming to that in a second. So there are a couple of more theories like likelihoodist approaches or fiducialist approaches. Now, somewhat more recently, but not that recently, we've got this whole new topic of imprecise probabilities, which is actually a whole range of methods, which I'll also be talking about in the next slide. And I've also included fuzzy set theory, which is really not a theory of statistics. It's more, it was intentional. Initially, it was intended as a description of an uncertainty stemming from human speech. So if I'm talking about a large number of apples, what does large mean? And that's what fuzzy set theory was intended to describe. But I'll be trying to cast fuzzy set theory in a framework of belief in this talk. Now, if we're talking about imprecise probabilities, it's not one theory, it's a whole range of theories. Usually, to start off with that, you can think of maybe an urn where you know that there's 3 blue balls and 2 orange balls in there, and 2 balls of which you don't know the color. They could be either orange or blue. Now, what's the chance of you drawing an orange ball at random that would be anywhere between 2 and 4/7? You could look at this differently, saying that if you've got the probability that a random variable assumes the value 1, 2, or 3, then you've got this triangle here where every point in this triangle represents a probability distribution. And now the creedal set of all probabilities with an expected value of less than 1.5 would be this blue area here. So imprecise probabilities is all about computing with these creedal sets. And then you have lots of theories that describe such imprecise probabilities. You have a very coarse theory would be sets and intervals. And now in a loosely defined increasing order of generality, you could then talk about possibility theory, which I'll be doing today. P-boxes, both of them are generalizations of sets and intervals. They're not really comparable because they express the information differently. If I were to make a definitive statement, I would probably say that P-boxes are a little more general. In any case, both of them are special cases of Dempsey-Schaeffer theory of evidence, which itself is generalized by capacities, and then we go to lower provisions and so on and so forth. So we see that possibility theory is more on the lower end of generality, and nevertheless, the intention is to convince you that possibility theory is actually a useful language, not just to describe imprecise probabilities, but also to describe confidence. And I'm probably not going to have enough time to talk about this, about predictions, and they're all connected. I'm mainly going to be talking about the connections. So basically, I'm starting off with the basis of possibility theory coming from fuzzy set theory, a mathematical basis, and then I'll be connecting this to imprecise probabilities and to frequentist inference in the framework of inferential models. So if you want to take anything away from this talk, just remember this key message that possibility can be used for imprecise probabilities, confidence, and predictions. So let's start off. What is possibility theory? If you're just defining possibility theory from an axiomatic basis, fuzzy set theory starts off with talking about, so consider a standard set, subset A of the universal set omega, with some crisply defined boundaries. So then you can define this indicator function chi, which is either 0 or 1, depending on whether some element is inside or outside. And then you can sort of fuzzify this and give this a 0-1 interval valued membership function, where the membership values couldn't be anywhere between 0 and 1, 0 being outside, 1 being certainly inside, and anything in between. Now, this membership function, I usually define it to be measurable with respect to the measurables, to some measurable space, and normal. This is somewhat important, this assumption. And then from that, you can define a possibility measure just by saying that the possibility of some event, in the event coming from the sigma algebra, is the supremum of these elementary memberships or elementary possibilities. So you could also say that the membership function is an elementary possibility function, because you see that if E is an event that contains only one elementary event, then the possibility of that is exactly the membership value of that event, elementary event. And this possibility measure has a couple of properties which look similar to the Kolmogorov axiom. So pi of the empty set is 0, pi of the universal set is 1, and then we have this maxativity property. If you generally speaking, if you replace the supremum here by a sum, then you would sort of arrive at the Kolmogorov axioms if those events are disjoint. Now we have this maxativity. This measure is also monotone, but it's not self-dual. So the possibility of the counter event is not 1 minus the possibility of an event. For this, we can define the necessity measure, where the necessity of an event is just 1 minus the possibility of the counter event. And then we have some similar properties. And necessity measure would usually then fit into the framework of amonotone measures or so. However, all the information, the possibilistic information, is contained in the membership function. The membership function is really what we want to be computing with. And the membership functions are important because you can look at them in a variety of ways. So you can always talk about the elementary possibilities of, every element has this elementary possibility or membership. You can talk about its super-level sets, sub-level sets. If you're a random set guy, you could talk about these focal sets with this basic probability mass. And what you can also do is you can talk about it in terms as being a random variable, because by the definition, the membership function is measurable. So it's really nothing other than a random variable. And this is perhaps the most important concept of or interpretation of a membership function. So now I'm going to be talking about membership functions, and I'm going to be calling them lowercase pi, but this is nothing other than a membership function. I'm just now calling it lowercase pi to denote that it's an IP description. And so this is a random variable. And now this links, this view as a random variable links possibilities and probabilities in a very nice way, because now you can define consistency between a probability and a possibility by stating that these two are consistent if the possibility is an upper probability. That is, it bounds the probabilities of all events. This is equivalent to necessity being a lower probability, and then you have this connection to the theories of upper and lower probabilities or imprecise probabilities. And maybe the criterion that's most easy, or that's easiest to check, is by saying that the membership function has to be a super uniform random variable. That is, you can just say it has, obviously being a random variable, it has a CDF, a cumulative distribution function. And now basically it's 0, 1 valued, and you take as a reference the uniform distribution. And now if that cumulative distribution function runs below the CDF of the uniform function, then the membership function stochastically dominates the uniform CDF, or a uniform random variable. Therefore, that's what I was saying, is it's super uniform. And you see here that usually for one possibility distribution, you can find many probability distributions that make the membership function a super uniform random variable. So you can define a Creedle set as the set of all probability measures that are consistent with the membership function, or with this IP description. And now this is why I'm calling it IP description, because one membership function defines this set, which is usually, it's never empty if it's normal. And it's also coherent, meaning that the possibility is actually a tight upper bound on the probabilities in this Creedle set. So this is how you can link possibilities and probabilities, making possibility theory just in mathematical terms, without any interpretation of probability, a theory of imprecise probabilities. Now, the usual question is, okay, so now I have some sort of information about my Creedle set maybe, and I want to model that as a possibility distribution or an IP description. So usually you don't start with some pi, but you maybe start off with some set or family, P1 to P2, P3, and you want to model that. You want to find some IP description that is able to describe this set. So what you then need is the plausibility function, which I'm not going to go into detail. It's sort of, sometimes I like calling it a possibilistic prior, because it kind of gives the plausibilities this, it's the subjective part of possibility theory. You're basically free to define the plausibility function whichever way you want it to define. It only has to be a membership function again. What's usually a good choice is what I call optimal plausibilities. So basically defining the plausibility function as the pointwise upper probability of this family of imprecise probabilities is usually a good choice. And this basically gives you an order of how plausible you find the elementary events to be. And now with these two concepts, or these two objects, the family and the plausibility function, you can apply the imprecise probability to possibility transform, which then gives you an IP description that is consistent with all the probabilities in this family. It has the same plausibility order, and it's also maximal specific. Maximal specificity is not something that I want to talk about today. So the consistency is I think it's clear what that means. And the plausibility order you can see here. So again, this is, I have a random variable that could be 1, 2, or 3. And I'm talking about the IP family of all probability measures that have an expected value of 1.5. Now I can compute these optimal plausibilities, which are 0.25, 0.5, 0.75. And having computed these, I can now evaluate this formula here, which is basically just integrating the sublevel sets of my plausibility function, if you look at it, finding the supremum of the probability on these sublevel sets. And then I get this IP description or membership function on the right. What you're seeing here is the blue line is the original IP family, and the green area is the Creedle set of my possibility distribution. So you see that I'm not able to precisely model this family with possibility theory, which is why I'm saying that possibility theory is somewhat coarse. But this is, in a sense, the best possible approximation that you can find with possibility theory. And now coming back to this plausibility order, you see here that the elements 1, 2, 3 are somewhat ordered by their plausibility values being 0.25, 0.5, 0.75, and you find the same order, though not the same values, in the possibility distribution. So this is the imprecise probability to possibility transform. It's quite easy to compute. So in this case here, those are just basic linear programs, six programs that you can solve one after the other. So first you compute the elementary optimal plausibilities, which are just these, again, basic linear programs that you can solve with your favorite optimizer. And then the elementary possibilities, just again, integrating on the sublevel sets of your plausibility function. So this is the mathematical connection between probability theory and possibility theory. Now, recalling the earlier argument that possibility theory is a theory of belief, this is what I'm owing you. Now I kind of have to tell you how can I incorporate data in my possibilistic descriptions, because this is usually how our beliefs are formed. So say I have a statistical model of my observations, so Q are my observations, and I assume them to stem from some statistical model that's indexed by some parameter, which comes from a larger set, but I don't know which parameter is which. And observing, and I get one observation, and now I want to know what do I learn from that. And for this, Ryan Martin and Liu introduced this notion of inferential models, and basically saying that every data-dependent capacity, which is just a monotone measure in the sense on the measurable space, on the parameter space, is, in principle, it's an inferential model. So this could be a Bayesian or a fiducial probability, a belief function, a p-box, possibility, whatever you want. And now for this inferential model to sort of be good or useful, you have to follow the argument by Reed and Cox. It is unacceptable if a procedure yielding regions of high belief would, if used repeatedly, give systematically misleading conclusions. And they translate this to this validity criterion, where they're basically saying, okay, so this data-dependent capacity is sort of, it's an upper probability. And now, regardless of what probability is intended to model, a low upper probability should lead to us rejecting the hypothesis, right? Because low probabilities usually mean that something can't happen or can't be true. This is what intuition would tell us. Now, if our upper probability is lower than alpha, we want to reject that. Now here in this validity criterion, we're talking about the case where the upper probability is lower than alpha, even though theta is contained in our hypothesis T. And now basically what we want to do is we want to constrain the rate with which we make these false decisions, or with which we kind of reject this hypothesis. So this is basically very, very much connected to frequentist inference. And this is their validity property, because then they say, okay, so if this data-dependent capacity that we're talking about here has this property, then it's useful for statistical inference. This is just, for me, inferential models in a nutshell. And of course, I'm talking about possibility theory. So what I'm going to be doing is I'm going to be talking about data-dependent capacities, which are possibility measures. Now, I'm owing you the justification for saying that Bayesian inference has some drawbacks. So this is one of their examples. Basically, you're saying, okay, so suppose I have some object, which I for the sake of the argument, assume I know the velocity, I know the obstacle position, and I know the radius. And now I want to know if this object is going to collide with it. I don't know the position of the object, but I have some noisy measurements around the actual position with some measurement variance. And of course, collision occurs if my object enters this radius around the obstacle. Now, if you do Bayesian inference, really, it doesn't matter how you choose your prior. You will find this very counterintuitive result that if your on a collision course. So you see this, if you have a very low measurement variance, you will see that you're actually on a collision course. If you increase the measurement variance, then the probability of collision will decrease towards 0. So the logical conclusion is that you should, if you're an advisor for NASA, you should tell them to buy the worst possible sensors that they can find, because then they will X or rule out any sort of collisions because they have low probability, which is really not what you want, because this is, it goes against intuition. So now let's see if possibilistic inferential models can maybe do better. So now I'm going to be talking about data-dependent confidence distributions. Again, these are membership functions. Now I'm just calling them gamma because they're there to denote confidence, and Q is just the observation. So they depend on the observation that I'm making, but then they're, again, a membership function mapping from the parameter space to 0, 1, to the interval 0, 1. And of course, they induce this data-dependent possibility measure, which was the capital Pi before. And this is also the data-dependent capacity M that Ryan Martin and Martin and Liu require for the validity. And now the nice thing about these possibilistic, what I call these possibilistic inferential models or possibilistic IMs. Now the nice thing is that you can show that validity then reduces to this rather simple criterion where instead of evaluating all the possible events, you only have to sort of evaluate the elementary memberships. And this again looks very similar to our consistency criterion. So I would argue that this is simpler to evaluate. And the nice thing about this validity is then for possibilistic IMs that the super level sets of your membership function are classical 1 minus alpha confidence sets, and the elementary memberships are p-values for the null hypothesis that the true parameter is actually theta. So this is this view that I was mentioning earlier. The super level sets are, so 0.6 super level set is 40% confidence set. And this here is, for example, 1 is the p-value of x equals 1. So this is how you can define possibilistic IMs. Now the question is, how can you construct possibilistic IMs? And this is where the connection between possibility theory and between imprecise probabilities and inferential models occurs. No, sorry, I'm skipping stuff. So the most intuitive idea would be to just say, okay, so the likelihood function looks a lot like a membership function. And in fact, there are, for example, Wasserman and Denou, who both argue that the likelihood function should be a membership function. So let's investigate this. Suppose we build our confidence distribution just by taking, for example, here the relative likelihood function. So likelihood function normalized to 1. Now the question is this valid? Is this valid possibilistic inference? And unfortunately, it's not always the case. Admittedly, it's hard to find cases where this is not the case, and very often it works, but you can't generally prove that. So suppose, for example, here again the coin toss example where you're just tossing the coin once and then trying to decide what's the probability of success. Now the likelihood function for this is either, if you're observing 1, it's either the red curve, or if you're observing 0, it's the blue curve. So 0 being, let's say, heads and 1 being tails. And now you see that if the actual probability is 0.5, so if the coin is actually fair, then you have basically this CDF of your likelihood function, which it's basically all probability masses at 0.5. This is what you're seeing here. 0.5 always has likelihood 0.5. So you have this CDF, which has this very steep step here. And this is basically a violation of the validity criterion, because you can't have plausibility 0.5, confidence 0.5 every time, because that's with 100% probability, because you're only allowed to have it 50% of the time. However, many have noted this, for example, Schaefer, that Q renders theta more plausible than theta bar or whatever, whenever the probability of the former is greater than the probability of the latter. So you can really say that it's an indicator of plausibility, but not of confidence. And you should keep this in mind, because it's going to be, now I've already highlighted the plausibility, and it's also a reason why in the imprecise probability to possibility transform, I call the plausibility function a plausibility function, because we can use it there, because this is where our remaining degree of freedom is, so to say. Now, more generally, how can we construct a possibilistic IM? So how can we construct this confidence distribution here? Now, if we again look at the statistical model, this is again the statistical model, Q depends on P of theta. If we were to find a consistent possibility distribution of P theta, so also depending on the parameter, then the consistency criterion would read like this. And if we have a valid possibilistic IM with respect to our statistical model, then the validity criterion looks like this. So they're the same, just that these two terms here, they differs here. So the natural approach is to just exchange them. And this is what I call the pivotal step. So really it's, I always think of it as some sort of possibilistic likelihood principle, where you're just switching arguments and indices. And this is really all it is. It's a mathematical trick. It doesn't even, you don't even have to implement it. It's just the membership function. If it's parameter dependent, it's a function of two variables, of the parameter and of the outcome. And now the question is just what's your index and what's your argument? And the nice thing about this pivotal step is that we know from the imprecise probability to possibility transform how to construct such a possibilistic description. And now then the consistency directly implies validity, because then this is always given. And special cases are the CDF to confidence transform, the complementary CDF to confidence transform. So both the CDF of the statistical model and the complementary CDF, they both are consistent membership functions. So CDFs are always also membership functions, which are consistent with itself. And this is a very natural approach, because this immediately gives you, in the univariate case, these one-sided confidence intervals or one-sided confidence curves, and symmetric confidence curves if you have text, so to say, the symmetric CDF to confidence transform, which is just taking the minimum of the two and multiplying by 2. So these would be classical confidence intervals if you take the superlevel sets of these curves. So for example, the superlevel 0.6 superlevel set of the red curve would be a 40% confidence interval. In here, for example, in exponential sampling model, where you're trying to infer the rate parameter. So it's not so important that you understand these special cases here. It's just that you can find then, in this manner, you can derive or rederive many standard frequentist confidence intervals or hypothesis tests. What you can also do, what I hinted at already, is you can combine the imprecise probability to possibility transform and the pivotal step, and that gives you the probability to confidence transform. So basically you're saying, okay, so my confidence distribution is just here with a pivotal step, the same as my possibilistic description or my AP description. And now I can apply the imprecise probability to possibility transform, which in this case, because I'm only transforming a singular family of probabilities, I'm only transforming this one probability measure, so I don't need the supremum. It's really a probability to possibility transform, and it reduces to this expression here in blue. And now if I'm taking, for example, the likelihood function as my plausibility function, then this gives me, this resembles sort of the likelihood ratio tests, which is in many respects optimal. If you can compute it, then this is usually optimal. And so this is the probability to confidence transform, which allows you to directly from a given statistical model compute this membership function. It's just this integral here. And of course, to compute that, you can do a basic Monte Carlo approximation. So you just sample from this statistical model here. So you take some Monte Carlo samples and Monte Carlo samples, and you count the number of Monte Carlo samples that have lower plausibility than what you observed. There's also a reliable variant that's relying on the beta distribution. I don't want to go into detail about that, but it's a little more reliable. And what you see here on the right side is that with an increasing number of Monte Carlo samples, you get very nice results. And basically, the idea of this reliable Monte Carlo approximation is that you make sure that you account for the error that you can do when Monte Carlo sampling. And there's also an interval extension based on a reweighting idea by Fitz and Guggenberger. So this is the probability confidence transform. And now what does that mean? So how can we interpret that? So let's take I think it's quite a famous XKCD comic and stirred some discussion. So it's the age-old question: did the sun just explode? I think it takes 6 minutes for us to know, but this neutrino detector might know earlier because it can detect these neutrinos, and then basically they've constructed this detector in such a way that it knows the answer, then rolls 2 dice. If they both come up 6, it lies to them. Otherwise, it tells the truth. So they try it. The detector says it has exploded. And now the joke is that the frequentist statistician says that the probability of this, the p-value is lower than 0.05. So he concludes that the sun has exploded. And the Bayesian statistician says that he bets him $50 that it hasn't exploded. So how would we do this in possibilistic setting? So we have our 2 parameters: the sun has exploded or it hasn't exploded. And we have 2 observations. So the detector answers yes or the detector answers no. Our statistical model is this here. So the probability of the parameter matching the observation is 35/36. And the lie obviously has a probability of 1/36. If we do a probability to possibility transform of this, then we get this model here. So basically, this is just shifting the larger value to 1 and keeping the lower value. And now, again, we can so we know that we observe yes. Here the detector says yes. So this is what we care about. And we look at the confidence distribution that it gives us. So basically, the confidence in the parameter is that the sun has exploded is 1. The parameter or the confidence in the hypothesis that the sun is not exploded is 1/36. So if you're an IP guy and you're into betting, then you would say that if he throws $50 into the pot saying that it hasn't exploded, then you're willing to throw in up to $1,750 saying it has exploded. And you would consider this a fair bet, or I would consider this a fair bet. Okay, so this is maybe how you can think about this. What's even more relevant for practitioners is what I call the possibilistic inference principle, and this strongly resembles the A, P, and C step of Ryan Martin and Liu for deriving these confidence curves, so confidence distributions. So obviously you can just do the probability to confidence transformation, but sometimes you might be able to write this as a sampling model with a pivotal quantity or in a pivotal way. So basically what you do is you find an implicit relationship between the parameter, some pivotal quantity of which you know the distribution, and the observation. So for example, say you want to estimate the mean of a Gaussian distribution here, you know the variance, then you can write this association in this way. And you have this pivotal quantity of the standard normal distribution. Of course, there's an infinite number of associations that you could have, and some are better, some are worse, but it doesn't. So from a validity point of view, it doesn't matter. From an efficiency or a specificity point of view, it does matter. But you're on the safe side, let's say it like that. And now what you do is a prediction of your pivotal quantity. So basically what you want to do is you want to find a consistent IP description of your pivotal quantity. So this lowercase pi of u. And then you can basically just compute the extension under the sampling model from the pivotal quantity onto the combination, which is what's happening here. So say you've observed Q, then this is basically just the extension that you compute. And now the extension, I talked about this in a talk almost 2 years ago now, or 1.5 years ago, also at the Risk Institute. So I don't have the time to go into detail about that. So you're welcome to watch this talk, where I talk about the extension a lot. Basically, the takeaway is that you have a variety of ways how you can compute the extension. It works, for example, for the collision example that I showed here, where again, so you have this object, kind of weird assumptions, you know the velocity, but you don't know the position, but you can measure the position. So what you could do is you could just say your measurement gives you the origin. And now what you can do is you can just sample around the origin, and at every point you just compute the probability to confidence transform. So now the color really indicates the membership here. Yellow is close to 1 and blue is close to 0. Now what you can do is every one of those samples you just propagate through this function here, this minimum function. So basically you just compute this value for every one of those samples, all the other quantities in there you know, and this gives you such a membership function. So this is basically a representation of the membership function with samples. You can think of it like a tablecloth. If you drop it from above, then this gives you the membership function. And now the nice feature about this possibilistic IM is that it still says if you have an arbitrarily low variance, then you know that you're on a collision course. This is still given. However, if you increase the variance, then the possibilistic IM simply tells you that the information is too coarse, or that you can't use the information to make really useful inference here. The lower probability of a collision is 0 and the upper probability is 1. So you can't really say anything. It's just too imprecise, the measurement. So this is what I then would call reliable confidence instead of the false confidence that we had earlier. Now, I said that the assumption here is kind of weird, that you know the velocity, you don't know the position. In the real case, this is just as an outlook what you can do with this. You would be able to, so you would go about this differently. You would have a statistical model, for example, of your satellite orbiting the Earth. You get at various time instances, you get some measurements of angles, for example, how we're relative from the Earth. And you usually write this as a dynamical model. So this consists of the system dynamics of how the state of the system evolves over time. And the state could be angles of a robot, the orientation or the pose of the satellite, or maybe the concentrations in a chemical batch reaction process. And then you have some model of how you get your measurements from these states. So how these states generate your measurements. Now, if you cast this in a statistical framework, then you might say that here you have some process noise where you don't know if the system dynamics that you modeled are quite correct, or if there's some error in there. And you might also have some measurement noise. And this is then usually what you want to do with filtering. You want to still make inference about the actual or the past states of your system, or even potentially the future states, in order to predict a collision. For this, you would need possibilistic predictor models. I don't have the time to talk about this, I think. Really, it's really the same as an possibilistic inferential model. So basically, you're just saying I have two imprecise variables, some that are connected through these unknown parameters, and basically here is the semi-pivotal step, which gives you a way how you can compute such prediction distributions from confidence distributions and IP description distributions. And the feature of these prediction distributions, which are again membership functions, is that their super level sets are prediction sense in the frequentist sense. So they're not, yeah. If you've heard of that before. And now you can implement this in this sort of recursive way. So basically you're at every time instance, you compute a confidence distribution about where your system could be right now. Then you predict this through your system dynamics. You check this against the actual measurements that's maybe giving you a different range of values that could possibly contain your true system state right now. Obviously, the true state is going to be in the intersection, and this is how you go about this recursively. And then there's a particle-based implementation here, which now this is maybe the most instructive learning how this filter works. So you start off with the initial set of possible states about which you don't know anything. So blue here indicates membership 1 and white indicates membership 0. You start off with a whole range of positions and orientations of your system, and you don't really know what's the case. You propagate this through your system dynamics, you still don't really know much. Now you get the first measurement and you compare all of these particles to the measurement, and you check if this is sort of consistent or if it's commensurate or not. And then you have to do some updating. You want to do some resampling to focus on the particles that contain some information, so that have non-zero membership. And then you can again do a prediction at the next time step. And all of a sudden, after just one measurement, you have a quite good idea about where your system is actually right now. And this is very easy to implement. It's really just propagating the particles through your system dynamics and updating the memberships accordingly. And now if you apply this, for example, to a robot localization problem, so this is a robot that's basically trying to locate itself by just measuring relative orientations to 3 landmarks of which it knows the position, then this works quite well. So you say you start off here, and then it drives in this sort of infinity-shaped or 8-shaped trajectory. And then you see that this works quite well for different time steps. You see the different confidence distributions. Naturally, if you're inside this triangle of the landmarks, you get quite good ideas of where you actually are right now. And the further you move away, the coarser your inference becomes. So this brings me to the end of my talk. Don't forget the key message. Possibility theory is a description of imprecise probabilities, confidence, and predictions. So you can do quite a lot. For imprecise probabilities, it's a coarse theory, but I think for especially these possibilistic inferential models they provide a very intuitive approach to frequentist inference and these prediction and confidence sets. If you want to know more about it, you can read about it in a recent journal article in the International Journal of Approximate Reasoning, or you will have to wait until I've published my dissertation. And with that, I thank you for your attention and conclude the talk.
Thank you, Mr. Hose, for your wonderful talk. Really fantastic. Love the diagrams as well. I thought they were really excellently put together. Does anyone have any questions from the audience? Alex, would you like to unmute yourself and ask the question?
Yeah, sure. Yeah, thank you very much, Dominik. Good to see.
Alex. Good, nice to hear from you.
Long time no see. Nice to see some fuzzy stuff again. I guess my question is, going back to slide 7, and I don't know if this has been addressed in any of the fuzzy meetings yet. But
give me a second. I'm trying to, yeah.
Yes. Sorry. Was there just talking about the normal property of the membership function? Mm-hmm. Was there ever any consensus on what it means for a membership function to end up being non-normal? Because, for example, we were looking at some stuff in meta-analysis on like effect models in meta-analysis, and if you combine the effects of different studies in certain ways, you can end up with an output structure that is not itself normal. And to me, that kind of was a reflection of inappropriate assumptions of the way those effects should be combined. I just want to know what your thoughts on
so
the normal property word.
There are two answers to this question. First of all, if you're talking about possibility theory in the general IP setting, then, and you would just want to describe creedal sets of probability distributions, then you need the normality to assure that it avoids shared loss and it's coherent, because otherwise the creedal set is just non-empty. It's just empty. So this is from the purely mathematical formulation. If you're talking about possibilistic AMs, I've actually been able to find some papers where they also had this problem, and it doesn't seem to be a problem. So I've repeatedly had the same issue, that if you do inference and, for example, you combine various sources of information or two different confidence distributions that you've derived in independent ways, and now you want to combine them, and then you get these non-normal or subnormal distributions. It doesn't. I haven't been able to find a problem with that. So this is my conclusion. If anybody ever tells me what the problem is, I would be happy to listen, but I really don't know where the problem would be. So this is my takeaway of this from this.
So Alex and I are working on a similar problem, and I think part of the problem is about kind of what the evidence is. So if all of the evidence is on top of each other, like it's all in the same region of the space, then it seems completely reasonable to do any of these methods. But it seems to be when that evidence is kind of arbitrary and kind of there's bits and pieces all over the place, or when it might be might share some commonality, then they're the situations where I think probably because the idea of what we're trying to do, we're no longer making inference about a fixed parameter, we're now making an inference around a set of parameters, and I think that's where the problems fail. And I think well, that's what I've kind of convinced myself, that when so what Alex and I are talking about is we've got these confusion matrices from a bunch of studies, or I think they call it something different in medicine, but whatever, and each of them gives us like a sensitivity and specificity in a different part of the space, and when they're all overlapping, it's completely reasonable for us to just pull that data together and just get one confidence distribution or whatever for the joint set. But it's when they're not overlapping that we've got the problem. And I don't think possibility is the answer to that situation. I think, or at least we've not formulated it within the right set of assumptions to make it a possibility question, I think.
So would I agree with this, that the subnormality would usually indicate that there's a better way to do the inference. It's not necessarily that it's wrong, it's that it's there. You could formulate a better statistical model maybe to get something that's more, for lack of a better word, coherent, and that fits together better. But this is, and you could maybe take this as an indicator. I see that Ryan has a question.
Okay, so yeah, Ryan, would you like to?
He might also be
as well?
qualified to answer the question for subnormal confidence distributions.
Well, yeah. Well, first, I actually had another question, but I'll say something about this. But maybe first, let me just say thanks for great talk and letting me know that this was happening. It was great to get to hear some of these things again. So about this subnormality thing, I don't know that I can necessarily say I know the answer, but I've also experienced kind of the same thing. So I've been working on something. The specific situation I'm interested in was combining like a partial prior information with one of these inferential models that's already valid. And so how you might do something like this. So basically you have information coming, like says, okay, based on some prior experience, whatever, says that, parameters over here, and maybe here's a imagine like a possibility distribution that describes this prior information, and you also have your possibility distribution coming from the data, basically what you were working with here, and how might you pull those things together. And one question is like, how might you pull them together, and two, what kind of properties that it has. So I noticed that in your paper, your IJAR paper, you had this strategy for doing some kind of combinations like this, where you have two possibility distributions, and basically you can multiply them, or you can take like the max or something like that. So I was working with that and actually found the same thing that you found, is that you can actually prove that this, even though it's not normal, you can actually prove that this still satisfies a version of this kind of validity property. So I haven't finished that work, but I was also surprised by that, because I thought somehow this the non-normality should cause some problems theoretically, but I didn't find that. What I did find is that that kind of combination is maybe not the most efficient of the combination strategies, but definitely can preserve the this kind of validity property, at least in a certain sense. And so I'll have a paper about that I can share with you at some point.
This is so maybe just as a quick, quick side note. I had the very same results. That I ran some simulations, and I saw that basically you could say that this subnormality happens so little that it's not an issue. So basically,
that was also that was also my suspicion, was that it does cause problems, but at least in the case that I'm thinking, it's like the prior information is sort of real, and so then there is some kind of compatibility between this. So you're not running into this situation where like the prior says this and the data says this, and that you get this, extreme kind of non-overlap. So I think that's what's going on, is that this empty creedal set is just not happening enough to cause some problems. The question I was going to ask about was, I guess it's a specific one, but it's on your slide 19. Can you go to that one, please?
Yes.
This one? Yeah, so I guess I like to see, here this APC stuff comes up. So I think it was relatively recently, I wrote something about this, like mainly your version of the P step. So this like consistency part in the prediction. So this is actually a really clean way to describe this, I think. I guess my question, I'm curious what you, how would you explain this process? Like why does this make sense to say, okay, what I want to do is I want to find this possibility distribution that's consistent with this kind of known distribution of the pivotal quantity. Is there like intuition about how you would how would you explain to somebody that this is what you should do, is to achieve this kind of consistency property?
Okay, so the answer is kind of a long tour, and goes to these prediction distributions that I didn't really have the time to discuss. Basically, what I would say is that this IP description you can also think of as a prediction distribution in the absence of data, right? So you don't know anything. So this is your prediction distribution, which is fine because you assume that you know the distribution anyway. Yeah. And now basically the distinction between prediction and confidence distributions is somewhat arbitrary. So it's just what you could think about this here is sort of a confidence curve for you. So really what you can actually show that these memberships here are sort of p-values, if you want to say it like that, for your random variable or for your pivotal variable, and these super level sets are prediction sets. And now the possibility theory is all about this extension, right? Computing, extending the possibilistic information from one variable onto the information of the other variable, and you do that with the extension principle. So basically, it's really just, to me, this is like the possibilistic analog to Monte Carlo, really, just saying, I know the information from one variable, and I want to sort of shift this information onto the other variable. So really, Scott has this saying, which I don't know. It's I don't know. Yeah. So this is really the important part, where.
Okay.
you're basically extending the information from one variable to the other variable. This is how I would view that under the sampling model. I don't know if this is what you wanted to hear.
Well, no, I guess, I mean, basically it's that when we had a number of years ago, we kind of had formulated our version of this. That explanation of this kind of P step made sense to me, but I eventually realized it didn't make sense to anybody else. This seems simpler, and so I was hoping if there was some kind of easy way to explain kind of this shift from, okay, now I know this pivotal quantities distribution. I don't want to, you can't just use that. So if you just use this pivotal quantity distribution, you get like a fiducial distribution. You know that doesn't give you the kinds of things that you need in general. So then you have to do something, and so then we tried to explain why you should do this particular something. How the technical details of your explanation are nicer. So I thought maybe there'd be a way to kind of make this explanation cleaner, so that it would be easier for folks who are not involved in these IP things to kind of understand the transition. So I'm not expecting an answer. I guess that's just what I was.
I can try a different answer. So basically, if you want to hear it. So basically, here in the extension, what you're also computing is, like, remember the pivotal step, which is the shift of arguments. Basically, what you're computing here is, suppose if you knew the parameter, then you would here compute the, and you basically said that this was pi of q given theta, then you would here compute the possibility distribution of q, right? So this is sort of, and then you can think of this combination again as this pivotal step, where you're doing basically this likelihood step, just not in the density space, in the probability density space, but in the possibility space. So I'm usually saying that this pivotal step is sort of this likelihood step in the cumulative space, and this arguably is better because this density is sort of it's a strange construct that sometimes works and sometimes doesn't work, and so this is the explanations that I have in my head are kind of, I'm confusing myself here probably, and you more than it's helping, but
well, it's maybe too involved for this kind of discussion. Yeah. So I don't want to occupy all the time, and actually I have to go to another meeting. So okay. I'll give some other folks a chance. So yeah, thanks for having me, and thanks for trying to answer questions. We can connect on this maybe through email or something. So
thanks for coming though, and thanks for asking.
Yeah, nice to see everybody. Thanks.
Thanks. Matthias also left a comment about him leaving, but offering his congratulations for your extremely nice work. Do we have, I think we have time for one last question. Does anyone else have a question from the audience they'd like to say before we wrap up?
I just want to say hello to Dominik, and
hey, Marco.
I assume this is going to be like a preview of your dissertation.
Yes.
Defense.
So this is somewhat of a summary and somewhat of a preview. Yeah. So you can read about all of this in detail in the dissertation.
Okay, and then I wish you the best of luck for your defense, and congratulations on your work.
Thank you.
Okay, anybody else? And if not, sorry, my phone started listening all of a sudden. All right, so thank you very much, Dominik. Sorry, my computer's freezing up for a second, excuse me. Yeah, thank you very much, Dominik, for your wonderful talk. Congratulations again on completing your dissertation. Best of luck with the Viva. And we'll be uploading the talk onto YouTube. So if anyone would like to catch up on it or pass it along to anyone that couldn't make it, then I'll be sending out the link when we've uploaded it onto YouTube. So thank you very much again, Dominik.
Thank you. It was a pleasure being here.
All right. Thank you very much. Take care, everyone. Have a lovely afternoon.